Hello, welcome to another day of Physics 2. Today I'm going to finish chapter, oh, my numbering messes me up, 23, 22, 22, 23. Yep, today I'm going to finish chapter 23, which is the last chapter on the first exam. So I'll finish the chapter today. Friday will be practice problems. Monday I'll go over last semester's exam 1, or last year's exam 1 to show the type of stuff. And Wednesday will be some type of review that I haven't exactly worked out what I'm going to do with yet, because I have an extra day. And then Friday will be the exam. We've been talking about magnets. Here's my magnets. And generally, they go together, they stick together and stuff, and how in a magnetic field, so it's known as B fields, and how magnetic fields affect charge carrying particles, or particles with charge with some velocity. So we talked a lot about that if you have a particle with charge and has some velocity will feel a force. F equals qvb sine theta. And following the right-hand rule, hand in the direction of V, curl your fingers towards B, you get the direction of the force. This force is out of the page. But let's think about something for a second. If a charged particle feels a magnetic field, well, let's say we had a wire with a current running through it. A current carrying wire is just something with a whole bunch of charged particles moving down it. And if we have a current carrying wire, it's just, a whole bunch of charged particles. In fact, I can say using that equation, if I just multiply by 1 in the form of T over T, I could say this is the same as Q over T times Vt, B sine theta. But Q over T, that's how we defined current. And Vt will just be the length of this wire, because velocity times time is distance. And that'll get me to this equation. Any current carrying wire in a magnetic field will feel a force ILB sine theta. The current on the wire, the length of the wire, the magnetic field, the sine of the angle between. And this would follow the same right-hand rule. If the current is this way, I curl my fingers in the direction of B and my thumb is the direction. So this is also out of the page using the same logic. And so any current carrying wire will feel a magnetic field. For the direction of current, you mark the direction of the current, not the direction of electrons, because, all that backwardness. But any current carrying wire will feel that field. As I already said, right-hand rule works the same. You point your fingers in the direction of I, curl them towards B. So that's I, B is out. Oh, that's B is in, sorry, B is in. And your thumb points in the direction of the force. And so if I push up for that current and in, I get to one way. If it's going down and in, I get the other. You can actually show this explicitly. What I have right here is basically I've hooked this ball up to, this ball has a magnet in the middle, and I hooked up to a power supply. So I have current coming in down one ball, across this piece that's sitting on top, and out the other. I'm basically completing the circuit by going down this wire, across this ball, down this wire. And what's going to happen is that means it is a current carrying wire, and this magnet in the middle causes a magnetic field. When I make the current go one way, oh, I'm still drawing. When I make the current go one way, it moves one direction. When I make the current go the other way, which I just switched the direction of the current, it moves in the other direction. And that's all it is. I make it move by putting a current through this ball. As the current goes through the ball, it gets a force. Okay. So quick example problem. Let's say a wire carries a current of 10 amps in a direction that makes an angle of 30 degrees with a magnetic field of 0.3 Tesla. I should watch my sig figs there. Find the magnetic force, magnitude direction of a 5-meter length of the wire. So I'm saying a current of 10 amps, a magnetic field of 0.3 Tesla, 5-meter length, and an angle of 30 degrees. Now for direction, I'll just use the right-hand rule. and put my fingers in the direction of current, which once again, what I'm doing is probably backwards from the picture because of mirroring. I'm sorry, you can do it yourself. But you put your hand in the direction of the current, you curl your fingers towards B, which in this case is up, and your thumb points in the direction of the force. This force will be out of the page. As for the magnitude's ILB sine theta, which I can just plug in and get a value. Now, an interesting thing that can use it, and now for a practical use. And by practical use, I mean a very practical use of this. Let's say instead, I put a loop of wire in a magnetic field. And I'm going to say a magnetic field going to a right and a current as shown here. Now, this circuit doesn't really make sense. Really, there need to be a power supply. It'll probably look more like, a wire coming in and around with some sort of power supply coming off somewhere. But I'm ignoring where that power is coming from for now and just saying it magically has a current moving in a circle in this magnetic field. If I put this loop in a magnetic field, I can talk about the current, I can talk about the force on each side. Using my right hand rule, on the left side, the current is down and B is to the right, so the force is out of the page. On the right side, the current is up, B is to the right, so the force is into the page. For both, I can use my F equals ILB sine theta, and using my ILB sine theta, I and B are 90 degrees, so both sides it's ILB. You might notice I switched this to IBB just to be confusing. I'm just saying because the length of that wire is B. But the top, I and B are at 180 degrees. So the force on it's going to be 0 because the sine of 180 is 0. On the bottom, the angle is, that's a mistake. It says the angle is 90 degrees. I'm going to fix that real fast before I forget. Or not. Or my computer will freeze in place. Which is kind of like fixing it, only the complete opposite. Awesome. Do something, computer? Huh. Well, I'll talk for a little bit as I try to figure this out. But the bottom's at 0 degrees, not 90 as it's printed there. Hopefully I'll be able to fix that in a second, as soon as I stop pinwheeling. Okay, it is just PowerPoint that's messed up. Only the best lectures you get from me. Cool, and I can't force quit it. Okay, sorry about that. We will resume in 1 second. Don't know why that crashed. Might be because my computer's doing something else at the same time. Sorry. I already said I didn't know I was gonna do that extra day. The answer might be I might have to play catch up if I can't get my computer to open PowerPoint again. Only the best lectures for me. Almost there. Almost there. Oh, I'm sad. I can't even blame this when I'm teaching online because, this could have just as easily happened in the classroom. And it has before. It's probably because of this. Come on. Finish. Open. Okay, there we go. I was about halfway in. Well, I will just keep talking as I get this up. So what happens is because the code's going one way at the top, it'll have the force out of the page. Because it's going down the other side, it'll have the force into the page. Ooh, that was perfect. All that to delete a 9. And the top and bottom will have no force. There we go. Continuing. We're back on it. The top and bottom will have no force because they're parallel or anti-parallel. And so what's going to happen is if left to its own, this is going to spin. Because if one side is pulled one way and the other side is pulled the other way, it's going to whoop and go. And if you look at this from above, that's what it's going to look like from above. Is that there's a force is pointing as so. And so, yeah, this guy will spin. It'll create a torque. Torque just being RF sine theta. And as this goes, it'll start spinning and will keep spinning with once again a torque of RF sine theta. In this case, all being half of A. Now, as it spins, that's gonna that won't actually change the angle between B and F. They'll stay at the same angle from each other. But there'll be a net torque from the one side plus the other side, but both sides are the same. So a net torque of A over 2 F sine theta times 2, or AF sine theta. But that F, I've dropped a sine theta here. That F was ILB sine theta, though that theta was 0, so it's just ILB. And so the torque will be A ILB sine theta. But what I can do instead is say, you know what? A times L though, L was this length, lowercase b, A was this length, A times L is the area. So it will be IB times the area sine theta. Now, if instead of one loop, let's say instead of one loop, I had multiple loops, like, where's my slinky? Like basically it was like this guy, then instead of just one wire, it was a whole bunch looped together. Each wire would feel that torque. And so the net torque would be the number of turns times IAB sine theta. And this is what I'm trying to get with this. This is the important bit. If you put a loop of wire with a current in a magnetic field, it will spin. And you might think, well, isn't this going to go upright and then kind of stop moving? We'll get back into what happens in a second. But it will spin. And how much it spins is based off this torque. Now, this equation is important enough that we normally refer to it slightly differently. The NIA at the beginning, number of turns, area of the loop, current in the loop, which will all be basically set for the given loop, has its own symbol, mu, where mu is known as the magnetic moment. And if we plug in that mu, we just get the net torque is mu b sine theta. Now, really, this should be some cross products again. Mu should be a vector and b should be a vector. I'm kind of glossing over that because we don't have the math required. Officially, the magnetic moment is a vector and the direction follows a different right-hand rule. If you want to know the direction of mu, curl your finger in the same direction I is, and your thumb points mu. So like for my upper picture, I is going counterclockwise, so mu is out of the page. And the angle in question is the angle in between mu and b. That's the theta here. Now, why this is important? I'm saying you put a current through a loop of wire, it spins. There's a word for doing that. It's called a modal. This is how you make a modal. what motors do for the most part is you put in electricity, you get movement. You plug in power, the wheels go round. And that's how you can do this. An electric motor is a way to convert electrical energy to mechanical energy. And all you do is you put your loop of wire and set it up so that it can spin freely in a magnetic field. You put current in, and it goes. Now, there is one issue with this, the DC versus AC. Let me start with this right here is a DC motor. It's hooked up to DC power supply. And what's going to happen is I have these magnets sticking up, and these things that wrapped in like red shrink wrap, those are just the coils of wire. When I put current in, it spins. The second I put current in, it spins. Because that's just my motor. I forget what this one is. This is a close-up version of it. And you can see that I have a weird little split in it right here, that there was a spot that is not filled. That's because for a DC motor, you need something called a split ring communicator. That's what that is. The reason why is the current is coming through this, touching the metal, then coming out the other one. And what happens is, okay, when if you just kept this as is, when the loop turned 180, it'll then turn and go the other way. And instead of spinning, it would flip, then flip back, then flip, then flip back. What a split ring communicator does is it makes it so, and this GIF in the bottom shows it, is that the current in the loop actually switches every 180 degrees. Because even though the current going into the circle isn't changing, is that it's good, like right now the current's going into the top, but as it flips, it's still going into the top. It's just what is top changed. And by allowing this to not be fully connected but split, you can make it so that the torque is always in the same direction, as opposed to naturally where every time it does a 180, it would flip directions. That being said, if you make this an AC, you can make this work even better. An AC motor, the current switch happens naturally. Nikola Tesla made the first AC motor in 1887. It is thought to be one of the top 10 discoveries of all time. Hence, part of these magnetic fields are named after him. And it's just a motor that you put in electricity, you make the thing spin, like so. Any questions? Got all flustered with my computer not working. Okay, let's do an example. So, I got a circular wire of loop radius 1 meter. Is placed in a magnetic field, magnitude 0.5 Tesla. The normal of the plane of the loop makes an angle of 30 degrees of the magnetic field. The current is 2 amps. What's the magnetic moment and the torque? Magnetic moment, NIA. So if I want to, and the torque, mu b sine theta. At this point, it's just plug and chug, right? Here's the information I know. A in NIA is the area of the circle. So I do need to know the area, but it's a circle. The area is just pi r squared. And so mu is just Ni pi r squared. Now N, it's 1 turn, so N is 1. I will be the current, which was given, pi r squared. There's the magnetic moment. You want the torque? Torque is mu b sine theta. Questions?
That was pretty straightforward.
All right. Okay, let's do one other level of complication. Not really level of complication, but just one more bit to it that's kind of important. That I think the rest of this class is all going to be on basically the same idea in slightly different directions. So, if I have a magnet and a second magnet, they apply a force to each other, right? This magnet applies a force to that magnet. We also know a current can carry a force from a magnet. So, if a magnet is affected by a magnet, and a current carrying wire is affected by a magnet, logically, there should be some leap in logic we can make that a current carrying wire is a magnet Like, if magnets are affected by magnets and magnets are affected by current carrying wires, is a current carrying wire a magnet? And the answer is yes. Any current carrying wire is also a magnet. And that's part of the reason that current carrying wires are affected in magnetic fields. You see, if you just have a wire not with no current in it and put compasses on it, the compasses will just line up with Earth's magnetic field. But anytime you have a current carrying wire, the magnets will line up in a circle around it. And for a long straight while, there will be a magnetic field that circles it. I don't have. Did I not film that? Sorry. I should have a film of that, but I don't see it. This is. Yeah, nope, I didn't film it. Okay. Um, yeah, for any straight current carrying wire, the magnetic field will be as follows: mu naught I over 2 pi r. In this equation, mu naught is known as the permittivity of free space. When dealing with capacitors, we had epsilon sub naught. Now we have mu sub naught. Epsilon sub naught and mu sub naught are very related. We're going to get to that later on. And the two are incredibly interlinked. But where epsilon sub naught was used to explain electric fields, mu sub naught is used to explain magnetic fields, where mu sub naught is just 4 pi times 10 to the negative 7 Tesla meters per amp. In that I will be the current in the wire, and R will be how far away from the current. Because really, if you have a current carrying wire, the magnetic field is all the way going outside of it, just getting weaker and weaker as you go. But you can kind of view it as cocentric rings. And with this, we can find the magnetic field of any current carrying wire. Now, direction, we're going to find direction the same way we work out every other direction in this chapter. Another right-hand rule. You want to know the direction of the magnetic field around a wire? Point your thumb in the direction of the current. Whichever way your hand curls, that's the direction of the magnetic field. Now, as I said, it is making concentric circles. If you have a current carrying wire and want to look at the magnetic field, I could really say, I have like a near infinite amount of them circling it. And actually, if you just look at a wire and just work 2D, like my picture to the right, I'd say if the current's up, the magnetic field is out of the page on one side and into the page on the other. And so it would look like it's circling it, in this case like that. And same idea as before, if we put iron shavings around a current carrying wire, you can see the iron shavings line right up. Now, let's think about this. A current carrying wire creates a magnetic field. Current carrying wires are affected by magnetic fields. So we once again have well, I guess this has to work. If you ever have two current carrying wires, they'll start attracting or repelling them. If they're traveling in the same, if you have two current carrying wires next to each other, they're going to suck themselves closer and pull themselves together. If you have two current carrying wires in opposite directions, they're going to push each other apart. This is something in fine electronics that you really got to deal with and worry about. This is why a lot of things they talk about electric shielding around wires. The point of electric shielding around wires is basically to make a Faraday cage to stop this from happening. But if you put two wires next to each other, they will be attracted or repelled depending on the directions. And we can work out the directions just by saying, okay, this one has a magnetic field. The magnetic field goes this way, current's this way, and use both right-hand rules as displayed here. That literally is my hand. I took pictures of my hand to make those to show how it works. In fact, let's just do the math. If we have two parallel ones, if I have two parallel current carrying wires, each one has a magnetic field of mu naught I over 2 pi r. And I'm going to say they're separated by a distance d. I should have put a d in both of them, but apparently I didn't. If they're separated by a distance d, the force between them, well, the force on 1 from 2, the force on 1 from 2 will be the current on 1, L, the magnetic field of 2. If they're parallel, the angle is actually going to be 90 degrees because the magnetic field, as you can see drawn here, will be straight out. And therefore the force on it, I'll just plug in for B2 the value above. Now, this is force over length of the wire. People normally talk about the force per length, the force divided by length, just to say, you know, depending how long it is, that's how much force it is. But you can get an exact equation for the force between them. Okay. Let's do an example. This example is pretty similar to the one on last semester's exam, but not quite exactly the same. So we have two straight wires, 1 meter apart. They each have a current of 1 amp going through it in the directions indicated. What is the magnetic field halfway between the two wires? And if a proton moves at 2.5 times 10 to the 8th meters per second to the parallel to the wires at a distance of 1 meter from the wire to the right, what's the force acting on it? Now, this only asks for the magnetic field between them, but let's look at the magnetic field everywhere. If I want to find the magnetic field, I will use my right-hand rule. Let's start with the first one. On the first one, if I do the right-hand rule, bring my thumb in the direction of the current, I'd say on the left side, that's out of the page. On the on the right side, that's into the page. And all the way on the right, that's still into the page, right? Because it's still on the right-hand side of that guy. Now, if I look at the current from the second one, on the second one, on the left, that's out of the page. Still on the left of it, so that's still out of the page. And on the far right, that's into the page. Now, the magnetic field for them will be mu naught I over 2 pi r. But we're saying at the midway point for part A, if the midway point means the same distance from R1 is from R2. And the net magnetic field would just be the sums. But they're pointing in opposite directions. And even if I plug in the whole thing, there's going to be no magnetic field in the middle. That two current carrying wires, if you can keep them from sucking together, because that's really what happened is they'd suck themselves together. If you can keep them from sucking together, they'll have no magnetic fields in the middle because they'll cancel each other out. Because one will be one way and one will be the other, canceling it. Now, part B was what's the force on that proton? Proton? If I want to find the force on the proton, I need the magnetic field out there. And the magnetic field would just be the net magnetic field. But both of them are pointing in the same direction. So I'm just going to add them up. Now I have to notice because they aren't the same now. I say this is 1 meter to the right of Y02. So R2 for I2 will only be 1 meter. But the first one, R1, is going to be 2 meters because it's a meter to the first wire and then a meter after that. For B total, I is the same in both cases. Mu naught and 2 pi is the same in both cases. So I can factor those out. Don't forget that mu naught is 4 pi times 10 to the negative 7. And I can plug in my values. 1 over 1 plus 1 over 2 is 3 halves. My pi's cancel. I can cancel out I got a 4 on top and a 2 in there and a 2 over there, so I can cancel out my 2's. Leaving me with some units that cancel. And it's 3 times 10 to the negative 7 Tesla. No calculator even needed. But that's not the force acting on the proton. That's the magnetic field. Now that we know the magnetic field, we can get the force. Because if I want to get the force, I would say the force is QVB sine theta. And assuming I know the charge of a proton, which I wrote on the bottom for some obscure reason, I can say the proton's going up, the magnetic field's straight out, so they're 90 degrees from each other. And so the force is QVB, which plugging in values gives me a force. As for direction, direction is right-hand rule. the charge was going up, B is into the page, the force is to the left. And so this is my force. Okay. Now,
All right.
a practical use for this, kind of practical. Well, it's practical to some people. I'm a little too much of a hippie to find it as practical as others do. This is what a railgun is. Like, literally, all of this is what a railgun is. A railgun, which are used to fire projectiles really fast, is just a loop of wire where two wires with a piece that can move in between. Kind of like this guy here. A railgun is basically that, but the piece that moves is stuck between the balls instead of on top of them. And what it is if you take this setup, this U setup, and you put a current going in one thing through the middle called the armature, and then back out the other one. The two longer side pieces are each going to create a magnetic field. Creating the magnetic field, that magnetic field is going to be pretty large in the middle, with the magnetic field being mu naught I over 2 pi r from each one of the sides, those two sides. The piece in the middle, that has the current going through connecting the sides. And so since it has a current, it's going to feel a force. That force is going to make the piece in the middle move. Now, since all the angles are 90, I can say at a point in the middle of the armature, at its halfway point, it's the radius in the magnetic field is just L over 2. And if I solve for the magnetic field there, my 2's cancel. But that's each rail. So since that's each rail, there's twice as much. And I can say since the force is ILB, the force is going to be IL times that. I'm going to multiply together my I's, cancel out my L's. I plugged in my mu naught for some reason. Oh, just because things cancel. And you get an equation. This is a way to fire something really fast with just a bunch of electricity. Since it goes by current squared, if you make one of these and just put in a lot of current, you can launch something. Now, for the record, I made some approximations. This is the force acting only on this point right here. It is not incorporating the force from here to here or the force from here to there. If you actually do the force over the entire thing, this is the magnetic field as opposed to what I said the magnetic field was. But let's be honest, this is a lot nicer than that. So let's stick to my approximation for now. But that force, most railguns use about 1,000,000 amps. What you do is you charge a capacitor, a big one like this guy, and you set it to discharge. And what you can do is you can fire something about 23 miles per hour at about 7 times the speed of sound. So when I was in undergrad, we had to do like a capstone project, and one of my friends decided to make a mini railgun about yay long, firing small metal BBs. And what you do is he basically set it up just like this, and he just jammed the metal in like tight-ish here so that it created the circuit and the force would eventually shoot it out the end. And how he decided to measure the muzzle velocity was he went to the bottom of a spiraling staircase with a skylight above that was 4 stories tall. And his logic was he was going to shoot it straight up, and he had a bunch of cameras marked, and he was going to figure out exactly how high it got. From figuring out its height, he could figure out the velocity. He hit the top window hard enough that the noise, I was there when he was doing it, The noise made us think he broke the window. Luckily, he didn't. It would have been bad because it was the window in the physics department. They would have been pissed at us. But it went up so fast that even went up 4 stories for this little tiny BB without anything issues at all. This launches things and is commonly used in more. Damn it, mouse, show up. My mouse just disappears when it's on that screen sometimes, and is commonly used in various types of modern day projectiles. Because yeah, it can fire a heavy thing really fast. Okay?
All right.
So, last semester I had a student who kept trying to convince me to make one, but I refuse. Okay, it's actually not hard to make though. So, if a current carrying wire has a magnetic field, let's go back to that, right? So I got my current carrying wire here, magnetic field around it. Let's say I lay down 4 current carrying wires, like so. The orange one will create a magnetic field out of the in my circle will create a magnetic field out of the page. My brown one would also be out of the page. My blue one would be out of the page. My green one would be out of the page. That each of these wires will create magnetic fields as shown. And what I'm getting is if I put these wires in a square, they're all going to add up magnetic field in the middle. Let's say instead I just make it a loop of wire then. Oh, these came out of Odal. Sorry. Let me go back to this guy because the Odo's out. I would say for this first bit, the magnetic field from each one is mu naught I over. Oh no, this is right. If I do a loop of while, I could approximate this. Now, really, I'm making some assumptions here that I'm going to gloss over purposely. I mean, my equation was mu naught I over 2 pi r. And if I say if I have 4 of them, this should just be full mu naught I over 2 pi r. Which should be 4 over 2 pi. So 2 over pi. Oh, 2 mu naught I over pi r. It ends up actually, though, if you make a solid loop, it ends up the pi's cancels out, and you get this equation. That if you have a loop of wire, it ends up being mu naught I over 2o for one loop. If you have multiple loops, once again, like my slinky, it ends up being n mu naught I 2o, where n is how many loops it is. Once again, how to come to that equation would involve some calculus that I'm not going to do. But it ends up that if you make a loop of wire, since each piece of the wire, if I go around with my hand, since each piece of the wire creates a magnetic field in the same direction, it's going to create a much bigger magnetic field. And of course, there's a right-hand rule for this. If you curl your finger in the direction of current, your thumb is the magnetic field. But what happens if you have a loop of wire or multiple loops of wire? You'll get the same magnetic field lines as a ball magnet, with the magnetic fields going up through the middle and then around the edge. And it ends up that a loop of wire, magnetic field-wise, looks the same as a ball magnet, where a loop of wire once again has a magnetic field of n mu naught I over 2o. But this equation is assuming at just the center. That is the magnetic field at this exact center. It is not the magnetic field over here, or over here, or over here, but only in the exact center. But here's the thing. Let's say you add a lot of loops, and you add so many loops that the length of the thing is much, much larger than the radius. If you add enough loops that the length is larger than the radius, what happens is it'll start creating a larger and larger magnetic field. And when you start adding multiple loops, it becomes what is called a solenoid. Basically, if I put a current through this, it would be a solenoid. A solenoid is just a spring of wire with electric field on it. And if you add enough, the magnetic field, add so many coils, it gets larger and larger and larger in the middle. And if you add something so that the radius is much less than the length, aka, I mean, this isn't a good example because it's pretty wide. It would have to be something more like this here, where if I look at the length of this green thing versus its radius, the length is a lot more than the radius. If you do that and use some calculus again, this equation can change. And what happens is if the radius is much smaller than the length, the magnetic field becomes uniform inside. you can kind of see why on the picture to the right. That it's not going to be just at the center here's the magnetic field, but it will be everywhere inside will have a magnetic field. Where the magnetic field will be mu naught Ni, lowercase n. Well, n is the number of turns per length. aka how many loops does it make in a set length. The tighter the turns, something like this, weak magnetic field. Something like this, strong magnetic field. The tighter the turns, the stronger the field. And if we tighten the loop to have no gaps, there has to be shielding, or as you know, the current would just jump down, but there's no real gaps. We can reduce the magnetic field outside the coil. And what will happen is the magnetic field outside the coil will become very, very, very weak. And all of the magnetic field will be inside. And what this does is allows us to create what looks like a ball magnet, magnetic field wise, but will be really strong inside and off the ends and not cause too much outside. This is what an electromagnet is. An electromagnet, or a magnet you can just turn it off, is just putting a magnetic field and current carrying wire, but in a loop of it as a solenoid. And what happens is you can have something that has no magnetic field, and then once you put in the current, has a strong magnetic field. I turn it off, it's not magnetic again. It's a little magnetic because that's the whole idea with holding soft magnets. Because it did have a magnetic field, the spins won't instantly stop being aligned. It takes them a second. I missed. But yeah, that's what an electromagnet is. This idea of a current carrying wire in a loop. And we can find the magnetic field of any solenoid or any electromagnet using these equations. Okay? So that's the end of this chapter. But I'm going to spend a little bit more of my 8 remaining minutes to remind you once again, that's the end of material on this first exam. So I want to kind of give a rundown of what to expect on the exam. I've already said it's going to be on Banco Hall. It's already up actually, but you can't see it yet. But it is on Banco Hall. Here's the idea: 4 questions long. The first question will be from chapter 20 and will be either Coulomb force on point charges, or electric field from point charges, or something with like constant electric fields. But it's going to be Coulomb force electric fields. The second problem will be something with voltage and probably capacitors. It'll probably either be capacitors in parallel and series, or electric potential and electric potential energy of point charges. I might try to mix the two if I can. The third problem will be a Kirchhoff loop. It's going to be the longest problem. I'm sorry. Kirchhoff loops suck, as you're learning for the homework tonight. I'll try to make the numbers work nice. I will give almost all the points just for making the loops. If you correctly make your loops and junction equations and you don't have time to do the math, don't worry about it. Last semester, I want to say I made 3, I had solving for 3 cones, and I think I had each one with 1 point. So like I1 was 1 point, I2 was 1 point, I3 was 1 point, and the other 22 points was just making the equations. And the fourth problem will be for either force on a wire or force on a charged particle plus magnetic field from a wire or a solenoid, something like that. Basically a mixture of all the stuff we talked about here. To give you a rundown, those of you who've had me before used to me doing this. Those of you who hadn't, this is what I do before exams. Here's the equation rundown. So the first chapter, the second chapter, which also had capacitors. The fourth chapter, don't forget, in case I do the capacitors, you might need circuits in parallel or circuits in series. And for magnets, that's the stuff. Force on a charged particle, force on a current carrying wire, magnetic field from a current carrying wire, torque on a loop. I didn't put mu there. I didn't put in terms of mu. I don't know why. You might need mu also. And magnetic field from a solenoid. And know your right hand rules. I will usually ask for direction. I recommend basically making an equation sheet before the exam, even though it's basically open notes because I can't control that. Just because you don't want to have to flip through everything during the exam. It's good to have just small bits of information in front of you. You could use this slide, but I normally recommend making your own. It will probably be more useful than this slide. But that's where it's at. Okay. Otherwise,
Alrighty.
Friday we'll do practice problems. Tomorrow you have lab due. Tomorrow's lab will be put up, which is Kirchhoff loops. And
Perfect.
oh no, the lab due tomorrow is Kirchhoff loops, isn't it? No, is it the one up? I can't remember. All days lost all meaning to me. You can look online. But I'll stop there.
Okay.
Have a good day.
Yeah, you too.